It's my pleasure to introduce to you our first keynote speaker, Dan Ingall. Very special person to me. When I worked at Xerox Special Information Systems, I had the pleasure of visiting Xerox Park many times to transfer the Smalltalk system. And Dan was always a very fun person to talk to. I even got to visit his home when he had a party, and I'll never forget that. I left Xerox in 1992 and dropped out of software engineering completely and never looked at or thought about Smalltalk code for 20 years. But last year, I was curious and found out Smalltalk is still in use and still popular, and it's gaining in popularity. So I contacted Georg and proposed that we do a reunion event. And so we're going to have our reunion program tonight. But I was thinking, who would I want to have as a keynote speaker at this event? And the first name that came up in my mind was Dan Ingalls. So I contacted him, invited him, and he said yes, to my great surprise. I was so honored and happy that he accepted my invitation. Dan is currently a fellow at SAP, and I would like to introduce you to him. Please.
Inside the microphone. Can you hear this? Yep. Okay, just to get going here. This is Sweet Smalltalk synthesizer music, and this is something that we play with a lot. And let's see, change into the percussion is the first recording we ever did for music input, which was John Maloney flicking his coffee cup. So I've got lots of things to talk to you about, and many of them predate 30 years ago. But I thought, for those of you who aren't aware of it, that it would be fun to. Let me first give credit where credit's due. And I can't do all of this because so many people have contributed to Smalltalk from the beginning on. My mentors were Alan Kay and Don Knuth, and everybody has a literary mentor. Mine was Cyrus Harding. At Xerox, certainly Ted Taylor, Dave Robson, Diana Mary, and Glenn Krasner were in on all the original implementations. Adele and Larry Kessler also did a lot of the sort of higher level work. Larry did some low level work too. Mark Lenzner, when I went to Apple, he did a lot of like the spelling corrector and a bunch of other things. Bruce Horn and Steve Putz and Steve Savitsky. Bruce and Steve Putz were young students. They were part of our trying out Smalltalk 72 for a date. Steve Savitsky also worked with us for a little while. And Evelyn and Mike Malcolm were down south in Xerox and a part of putting Xerox out into the world. Then Squeak came about at Apple and later Disney, and John Maloney and Ted Taylor and Scott Wallace worked on the core of that. And then later Andreas Raab, who I'm so sorry he passed away this year. It was incredibly shocking. He was a young guy and a huge contributor. He did all of the wonderful work for 3D and Croquet and Squeak. And Yoshiki Oshima and Bert Freudenberg, who worked with Alan's group down south. And then Elliot Miranda and Vasily Baikov I wanted to mention just because they've done some really cool work that's been part of Squeak as well. And everybody in the open communities. And if I have any hope for these communities, it's they somehow manage to stay as close together as they can. I was sort of sad to see that it didn't seem to me that cleaning up STIC needed to bifurcate its community to do Faro, but let's keep things as close together as we can. So I thought I'd talk a little bit about where it all began. When I came to Xerox PARC, my most positive experiences with computers have been using APL. And this came about because Ted Taylor had been an intern at IBM and had a chance to use APL there. And so I found out about it and tried it out. And I just thought it was so cool to be able to type things like 3+4 and just get the answer right back. I liked infix. I liked garbage collection, just being able to do anything you want and have it all reclaimed. And I really liked the APL workspaces. So in APL, you could define all the variables you wanted and give them values. And if you saved your workspace and came back a week later, everything was just the way you left it. So you may notice some of the effect of that in small talks. So we wanted to do some sort of language like that that was extensible for media. So you could talk about points and rectangles and musical notes and scores. And APL was not extensible in that regard. It was really nicely polymorphic for arrays, but not anything else. And Alan talked about Ben Wakebright had a language called PPL, which polymorphic programming language, which did allow you to define new record types. But again, it was procedure-oriented, so you have this n-squared problem. Remember, there was no object-oriented programming then. That, if you keep adding data types to a system and you have to write a print routine, the print routine starts to have all these special cases. And some poor user who comes to add this new little fraction class has to edit that huge thing. And if he makes one false move, it'll break the whole system. So Alan had this notion. Let's see, I should mention Simula, which had a nice data model for simulations. And we really also thought simulations was where we were going. So Alan had the notion that you could do all computing just by sending messages between objects. And I think part of that came from a sketch that he did at the Stanford AI project where they were connecting disparate computer systems. And he's always talked in terms of everything you do in a program should be just like connected computers. And the one thing that worked there was sending messages. So we talked about a language that could work by sending messages. And a couple of our favorite sort of koans of computing were the list evaluator in a page and meta. I don't know if any of you know about Dal Shori's meta too. Really cool compiler. And it written in itself is about a quarter page. So really like these kernels. And Alan said, I bet we could do an evaluator for a message-oriented language. And then I said, yeah, show us. And so Alan went home that night, and he didn't come in for about a week. But when he did, he had, this was all handwritten, and this is sort of a transcription of it. It was what I needed to do to actually get to work on an interpreter, so it's not as clean and cool as this, but in some ways it's more accurate. So then I went home and didn't come in for a couple of weeks and did something like that in BASIC, and actually that became Smalltalk 72. So Smalltalk 72 was, I think, the coolest. So this is before 30 years ago, right? By some stretch. I think it was sort of the coolest scripting language that's ever been invented. And the basic idea is it's nothing but a token stream. Okay. So if you take this program, tell a turtle to go distance times 5 and turn j times 90 degrees. The way it worked was that it would take, when the first token it got, it would look it up in its context. And that would give it back something to, and along with a pointer to the next thing. And then it could look at this and do what it wanted with it. And in this case, if you see if this was an instance of a turtle, it would go down through. And these were little, so now we're into how you write code. This little eyeball says, look at the next symbol, and if it matches, then do this. Okay, so there's a conditional, and it goes into this subarray if it's true. And this is sort of pseudocode here. It would draw a line of length colon, and the colon would fetch the next value from the message stream. So now we're down in here, but we're pointing up there. So there is a stack here, and at each point in the stack, it's keeping track of where the PC is and what the current context is. And so you can see that with just those simple rules and a little bit of experience, we came to a style that was just like modern-day object-oriented programming, except that it was completely interpretive. And one other thing that's worth noting is that these were just, to was the verb to define something, like to walk is to blah, blah. And so if you were defining an actual object that you wanted to make instances of, you could declare here the instance variables. And there was, this predated JavaScript and Java by 20 years, but there was this little function here called isNew. And every context had a place to store something called self. When you got down to isNew, if self was null, in other words, if you had called turtle as a function, and if you had put this little guy in there, then it would create a new instance, store a pointer to it in the context, and now you were running with an instance. Okay? And it would return that as a value. So you could use these both as functions and as object creators. So that's how it worked. And the context of our work there was we wanted to build a computing system for children of all ages, and it's still that way. So we wanted things to be simple for kids to use. And let me just go away from that. So I have a little simulation of all of that. Let's see here. This is the little scrolling listener. This guy here means I'm ready for input. It's a little picture of an alto. So we would, just to try the system out, we'd always type in 3 plus 4. And then we knew that most of the system worked. The next thing we typed in was I don't know if you guys can see that here. And this would test out all the floating point print routines, which meant just about everything in the system. So kids could write things like, let's see, smiley erased. So smiley was a global variable that was bound to a turtle. You could make lots of turtles, but this made it easy to just do one keystroke and have some fun. So we'll erase the screen there, and I'm going to shrink it back in again. So I would have this all in a nice window, but I did this for one of Alan's birthdays, and the date of the event came faster than the debugging could go, so I just barely got it running. But you could do things like 4i to 400 smiley, go I, turn 89. Okay, and let's see. You can do things like that. So that was the essence of it, and kids did all sorts of cool work in the system. And I'll just show you what the bootstrap looked like here. What I'm going to do is go. So the whole system was sort of written in itself. It was full of a bunch of these code escapes. So those are like Smalltalk 80 primitives. But you have to do that to get stuff going. So there was a pile of machine code in there. But for end user programs, as you see from the example of turtle code, it was all pretty clean. So you sort of pay your dues by writing a bunch of primitives. So I'll just take you for a little tour through here because it's sort of interesting. This entire bootstrap is 44K, and that's including all the comments. So here, these little tokens in the message stream, the colon fetches.
Can you expand the screen a little bit?
What's that?
Expand the screen a little bit.
Yeah, good idea. And go over here. Let's see. Well, this will be. Yeah. Is that better?
Yes.
Okay. And so I'll read anything that's important. So these are all the various message stream matching tokens. The eyeball looks to match. The open colon would fetch the next thing in the stream quoted. This would do a return. This would get the next token quoted. So if you said, this is called quote, it means next thing. So quote A, left arrow, 6, meant send the message left arrow to the atom 6, which did assignment. Okay? Like that. And this is the code for 4 that we just ran. And one of the things you'll notice is that there are a bunch of places where you can say for I to this or for I by that. So again, you have these sort of optional keyword parameters followed by tokens that fetch the associated values. What else can I show you? So here we get down into, this is class Atom, which was together with the context gives you variables. There was a class False. So everything was true except for false. Kind of following along by this. Hey, it works. But we changed that eventually, and I'll say more about that. There's also, then we've got vector and string. So those were both indexable objects, and numbers, and so on and so forth. And I don't want to spend a long time on this. Some substring code. Here's the class stream. It's very simple. It's actually, unfortunately, there's no comments in here, so. I think we had comments in there once, but Diana did a good job. She went through this bootstrap and put in a bunch of comments. This is class set. And then there's some programming support stuff, like this is the pretty printer, and there's the floating point printer, and then a whole bunch of text display routines. And Diana Mary worked really hard on this. So this has got several primitives in it for displaying text, for scrolling text, for clearing various areas of the screen and stuff. And then there's also a little programming editor that we did that lets you edit functions once you've typed in the definition of something. And it's got a sort of menu that lets you do insert, replace, and all that stuff. I was going to show that to you, but it turns out that there's some code right there, and I didn't want to have that happen here. So that's Smalltalk 72, and I'll just put that away. So there was a huge payoff to having that first interpretive language be flexible, because although it's just a token matching stream, it allows you to actually model message lookups. And it was live, so you got a response the minute you hit return. Actually, it was kind of leisurely, but within a second. So we did stuff at Xerox PARC. There was a serious lab called the Computer Sciences Lab, and their turnaround time for changes in their system were, minutes, hours, days on big things. And we were just there making changes and making changes. So we would go out for beer and have a good idea and come back and actually have something to see in an hour or less. So that was fun. And so we learned some real things. This do-it-yourself bootstrap, you've got to be willing to sort of pay your dues and write primitive code just to get it on the screen and get people actually using it. And in the process of using it, we really realized very soon that we liked this notion of keywords. It just made everything readable. Here's some statistics. There were 20 classes. I showed you a bunch of them. 200 methods, about 10 per class. 15K code bytes, and about a 30K image size. Couldn't be much more, because the machine wasn't much more.
So what did you run that on again?
So that was running on the Alto. Yeah, thanks. And basically all written in Nova assembly code. So I got the original thing running in BASIC, and then we got serious and wrote a Nova code interpreter. And Ted wrote the code for line drawing for turtles, and Diana wrote the code for scrolling and text display, an important thing. So we had this. The beautiful thing about being at Xerox was that we got to build something and use it and learn from it and throw it away and do a new one. And to me, that sort of parallels the scientific method, where you make an observation, you theorize, and you do an experiment, and you go like that. In software, it's more like this. This isn't exactly learning, but Smalltalk 72 was quite slow. I mean, really slow, as you can imagine, because it's just going interpreting everything again and again and again. So it's like parsing as it runs. It was not modular. This was a serious problem, because if you wrote some code that, for instance, added a method name to a class, and somebody else was using that keyword to recognize something else, it didn't work. In fact, it wasn't even readable, because if you read a piece of code, you couldn't tell how it parsed without seeing the definitions of the things that were running. So in that sense, it was a failure as a system-building language. Also, classes were not first-class objects, and nor were contexts. But we were sort of up against that. So we started doing hacks that would go in and find them in the heap and be able to get pieces out of them. So we could do sort of class-oriented programming. So from that experience, we knew what we wanted next, which was we wanted something that was readable and compilable for speed. We wanted classes to be real objects, and we sort of had a sense of how that would be, because we started thinking, oh, you could send messages to classes. Oh yeah, sure. And we wanted inheritance. If you would look really carefully in that bootstrap, you would have seen that there was copied code for vectors or arrays and strings, because it do the exact same thing. So out of that came the design of Smalltalk 76, which was an expression language with keyword syntax and infix. You would all recognize it immediately as Smalltalk 80. It had a byte-coded virtual machine, which gave us speed and space. And I was inspired by, I didn't know anything about it, except I heard Peter Deutsch was working on this byte-encoded list. And I thought, oh, that would be really neat. So I had this notion. And one of the I didn't bring any water. Maybe somebody could pour me a glass to bring it up. One of the wonderful things about working at Xerox as a sort of a hacker type is that the Xerox machines were microcoded. And it meant that if you could identify some little computing kernel, you could get it to run like 5 times faster than anything else. The reason being that in the microcode, you get a chance to execute 5 cycles of instructions on every memory cycle, which you needed to do because the memory cycles in those days were long. So a bytecoded VM sounded really good. And classes and context being real objects. So let me just show you that. So this is the paper that describes Smalltalk 76, and I'll just go through some pieces of it because you'd probably find them interesting. There's some sort of philosophical stuff. Here's some screenshots of it when it was running. So you can see we had Windows running there and text. And this was before we had the pinged browsers. So we would we'd have a class in each file. And that was actually kind of nice because you got this picture of all the code, or at least a significant part of it, sort of all at once. We had graphics there, so we had a neat bitmap editor, sort of a precursor of Mac Paint, done by Bob Flagle. There's a class definition, defining class rectangle, defining the origin and pointer. The character set's a little bit different, and that was one of the main changes to Smalltalk 80 was in order to go out in the world, we needed to deal with a normal ASCII character set. But you know, if you see things like this, adding points, pretty much like Smalltalk 80. I think that's, yeah, so what I want to show you is, so this was the sort of big aha about how we could run, apart from the aha that we could have this keyword syntax with the colons and agglutination. This is how the virtual machine worked and works to this day, basically. You know, so here's a class that points to a method dictionary, and it's got methods in it along with the source code. Basically, all that stuff is in Smalltalk 76, and here's the dynamic structure of a context that's got its pointer to the method and its PC. And a temp frame, stack pointer, all that good stuff. It all worked in. And the coolest thing, so that was that's one of my favorite things there. And another one is the fact that with context being real objects, you could actually write, apart from the fact that you could debug really easily, you could actually write a simulation of the interpreter. And here you'll see things like, so this is that slightly weird true-false thing, which is that if a Boolean was true, then it would enter this sub-piece of code, this block, and exit from the outer block. So this is basically a case statement. So it made things nice and terse and pretty iconic. Let me see, there's something that I want to show you there. If we get to the right one. Yeah. So, an interesting piece of Smalltalk 76 syntax that I think we should have kept for Smalltalk 80. There are a couple of them. One was that subscripting was done with a dot. And we could have kept, so it's an infix operator. And we could have kept that if we had used the @ sign. Okay? But there's a really neat thing in Smalltalk 76, which was that left arrow was considered to be a terminal keyword. So you could have, temp frame at low bits. That's an array access. Temp frame at low bits gets value is a store into an array. What's nice about this is that the left arrow comes with assignment precedence. Therefore, you can put over here temp frame dot low bits plus 1. So you can do that all without parentheses. And it was uniform, so you could put this, I don't know if there's any here, but you could say, you could have message pairs like next and next gets instead of next put. And you could do it with keywords also by having, I don't see one. Oh yeah, receiver inst field colon low bits gets value. So that's the message, inst field colon gets. And you could do that all nowadays with just using colon equals here. But that didn't happen. There's a similar thing like that that I suggested to Dave Unger for self, where it's actually more important because the way they do assignment. Okay, well that's what I wanted to show you about small parts. Yeah, so this kind of summarizes it. And if you don't have that, then if you're trying to do, A at colon I, put colon, and now you've got to put parentheses around the A at colon there. So it was readable because there was a parse, therefore it was compilable, and you could compile it into bytecodes. That's what we did. It was compact, therefore. And it had inheritance. I didn't mention that, but classes and had inheritance and polymorphism. And the early version was 50 classes, 500 methods, 20K code bytes, and 100K image size. And it really worked as a serious platform. We did document editor, that bitmap editor, and a serious IDE. So that was was right around this time that Larry did the Paint browser. And that really imprinted, or we imprinted on that. And it was a really good thing because everybody worked with sort of little browser pane size methods, which is totally appropriate. So at that time, there were also, I mentioned that Ted was working on the line drawing and Diana working on text, and we just, so this was the coming of age of bitmap displays. I mean, that was one of the big things going on at Xerox PARC, and one of the reasons that we were able to do that cool stuff that was, that most other computers didn't have such nice displays. The downside of it is that anytime you wanted to just draw a line, it wasn't a line drawing display, and you had to deal with all this junk about word boundaries and bit alignment and all that stuff. And if you looked at our code, so I guess the important thing that happened there. So another thing that's great is to be forced to move from time to time. Same thing with houses, but we wanted to get all of this to run on an 8086 when we built the note taker, which was a portable computer. We called it a luggable, sort of a suitcase thing. But it had an 8086 and actually had a couple of 8086s. And we thought, oh God, we've got all of this Nova code for doing this junk for line drawing and more Nova code for doing text and so on. We've got to rewrite all of that in 8086 code. And so that was what forced me to do Bitly, to just get it all in one place. And I started to see how if you set up all the conditions for the beginning and end of scan lines, and so on. You could do this is a model of how you can do bit copies without temporary storage. That picture just came to me. Actually, my kid has a rubber stamp that's a wheel. Called it. I was sort of thinking of that, or like a Xerox machine. But anyway, so all you need is just the registers in the machine, and that's all the temporary variables you need. Temporary storage. So we did BitLit, and that did all the hard work of scrolling and text display. We made up a special font that used it, and line drawing. And here again, there was motivation to do some small kernel because it would go into microcode, and then it would go fast. So it turned out that on the Alto, we could do all of the shifting needed in the process of doing the transfer under the memory cycle. So once you got it started on a scan line, it'd go as fast as the block transfer. Yeah, so that really was, suddenly made a bunch of things easier that were hard before, such as menus, and off-screen bitmap suddenly became easy. You sort of needed off-screen bitmaps because everything was still running slow enough that you couldn't just create a menu on the fly. So we do those by lit copies. Icons, sprites, windows, all that kind of stuff. And in the case of doing Smalltalk 78, which was on the 8086, it took our kernel from being about 26K of code down to about 6K of code, because it was mostly all in Smalltalk, calling BitLit, which meant that it ran a little bit slower. But one of the neat things about the note taker was it had an extra 8086 to run the disk and another one to run the ether. But we hardly ever had it on the ether, and that was a fast 8086. It was in 8 kilohertz. The other one was at 4. So I put BitLit into the Ethernet processor, and it had a little exchange protocol there. So we could actually, when it was displaying text, Smalltalk was figuring out where to put the next character, and BitLit was splitting the previous one. So we actually just about doubled the speed of that. I had a lot of fun with this. So one of the things that made it really easy to do is count bits. So you could go through an image vertically and get a histogram of the number of bits that are on. And so my father was a Sanskrit scholar, and he wanted to scan some text. So I wrote him an OCR program for it. So then once you had that, you could go this way and find the words. And then once you had the words, it turns out these are vowels up here, and there are vowels down below. So but anyway, you go through here and break that up and into the different characters. And, then I had a whole scheme for doing for taking a bunch of knowns and an unknown one and comparing it. Basically XOR, but there was a way of doing a better job of it if you cared. And then one of my crazier hacks was to do Conway's Game of Life using BitLit. So you can think of BitLit as being this huge parallel processor. And in Conway's Game of Life, you want to count the number of cells that are black, the number in all the neighboring cells of a given cell. And you can do that in bulk for a million cells by treating one bitmap as the 1's bit, one is the 2's bit, and one is the 4's bit in a number that is the number of neighbors. And then by shifting around, you can sort of do the equivalent of adding. So, yeah. So that's it running. We just started with a random pattern, and I'll zoom in on it. And if you play around with light at all, you'll recognize various things. Like here's a blinker, and one of these guys, and then you see these gliders going around. So this is 1,000. This is 1 million cells running, and it does. I've forgotten. I think it's about 60 blips that it takes to do a generation. Okay, so small talk 80. That's not supposed to happen. But it's actually made to not do that. I've never had it ring when the thing was set to not. Special feature of giving talks. So Smalltalk 80 was essentially a commercialization of Smalltalk 76, and the most important thing that was done was to go to the ASCII character set. The other thing that was done was to rework, have a real Boolean class, and that certainly cleaned up a lot of things and made it sort of more like normal programming languages. And I think what I'll do here is just to show some other fun stuff. Yeah, I know it. Everybody recognize that? Go away. So here we have a resurrection of the Apple Smalltalk, which began as Xerox Release 1. And Apple was a participant in this process that Alan Worksprock was talking about. They only got Release 1, they did not get Release 2. But Release 1 had no limitations on the license. And there came a time when I left Xerox and went to Apple, so that was definitely a nice feature. So we started working on it and improving it, and we put in a spelling corrector like version 2 only or whatever. And released it for almost nothing for anybody. And that's actually what we wound up using Squeak for, using to begin Squeak, because it was free from any licensing issues. So let me. Somebody say something about scrolling? What's that? So one thing to look at here is, so we had scrolling there, and these scroll bars, we wanted it to work for a one-button mouse. So there's actually 3 scrolling areas: down scroll, jump scroll, up scroll, and over here you get a menu. So that's how you get the menus. And I don't know, I'll show you. This image actually had some quick draw stuff in it, so I had to do some hackery to make it work. But I can go over there and say, good. Yeah. So that's all running in simulation mode. And then let's see, let's do this. Put that away for a bit. Nice color there. Sort of the archival color. And yeah, sepia tone. There we go. And then what do we got here? Let's do this. So there is the. This is the Xerox version 2 release. And let me. What you had to do when you got when you got this was you had to create the alpha file directory. So that's what this does. Actually, there's part of this that I haven't done, but and let's see what we got here. Animal objects, Boolean, logical operations. So if true, oh, that's unfortunate. It's kind of hard to read. Well, oh yeah. So here is true. Oh, so one thing that happened, I don't know if you remember this, but it kept a list of the file pages. So the first time you browse, if you browse to a class with a that's far in the alphabet, it takes it a minute to get there. So here is if true, return the alternative block values, and if false, that's the obvious other thing. So this is one of my favorite things. So in almost every language, if you need to define if you look at the bottom, it's still got an if. And message dispatch is more general than conditional. So there is no if at the bottom of this. It's just a message dispatch between true or false to the same method. So I think that's really cool in small talk. I don't know why. I just like to do this. You'll have to indulge me.
Your real desktop?
What's that?
Do you do that on your real desktop?
All the time.
Do the angles mean something?
No.
Make it spin.
We'll do that a little bit later. Okay. So we're going to come back here.
You just do because you can't.
Yeah, exactly. So let's see. Not long after Smalltalk, so I went to Apple and worked on the Apple release, and then I got beamed up to my family business in Virginia for 10 years. And near as I could tell while I was gone, not a lot happened in the software world, but the machines got so much faster. Couldn't believe it. And I came back, and we wanted to do. Well, I had a brief stay at a couple of other places, but wound up coming back to Alan's group at Apple, and we wanted to have a Smalltalk or some language or media that we would have complete control over, and Smalltalk was certainly a candidate. But again, we had from the Apple Smalltalk this pile of 68,000 code, and oh no, not another virtual machine to write. But the machines were so fast that it seemed that you could actually use them in simulation. Use a simulated Smalltalk. So we had this idea to do exactly that. There was the reference interpreter that Dave had done, and I guess all of us kind of chipped in on that. It's published in the Blue Book, and it turned out that Mario Walchko with his class in England, I guess, had actually implemented it. It had written, had typed it in. That was the important thing. So we had that copy, which had a bug or two in it. But anyway, so we actually got that running on VisualWorks, And so we were getting that running. We figured out how to get the sources inboard so that they were actually an inboard stream, so we didn't need a file system. And then, so we had Scott working on a new file system, and Ted worked on the storage manager, and I think the Suite storage manager is really beautiful. And then John Maloney started to work to do a translator from that version of the interpreter from Smalltalk to C, because it's written in a style that it actually doesn't need to do any message sends. So this is what we now call slang. So it's Smalltalk being used as a sort of a macro language that's translatable to C. And we had earlier experience with that. Ted Taylor did a virtual memory called Loom, which was all written in Smalltalk, and we wrote a translator from that to BCPL. So we had some experience that would work. So this was the most incredibly energetic project I've worked on. In 3 months, we got the whole thing going with sort of working just perfectly in parallel. And then another 6 months, we got it all finished and released it in 1996 as Squeak, and with real sound and graphics, bit identical behavior on all platforms, and I think Warplit and Morphic came along a little bit later. And it was also so neat that it was all described in itself. So because we just only had it running on the Mac, and it was in something like a couple of weeks that Ian Chimardo got it running on Windows. It's right on Unix, and then Andreas Raab, not long after that, got it running on Windows. So if you include all the details in the release, it really leveraged the open source community. So let me show you a bit about that. So one of the things I'm most proud of in this design was Ted and I worked on this object memory. It's a direct pointer object memory with just one word of overhead. Basically, we had a fancy header. So an average object had essentially just one word of overhead, which included storage management bits and a compact class index and a short form of an object format. So there was very little overhead there, and this was because memories were still small, and we knew we were going to 32 bits. But this wound up being more compact than object table implementations and more general. And then there were escapes, so that if it was not a commonly used thing like points and rectangles, then in general you could expand up and you could have super big objects as needed. And it used a generation garbage collection scheme like the one that we had done at Apple. But the especially neat thing about it was that when it would do an incremental compaction, it would also, incremental collection, it would also do an incremental compaction, which meant that the allocation was just like, malloc. So that made things really simple. So there were a lot of things that wound up really simple in Squeak. You can read all about it here. In BitBlit, we knew we wanted to do media, so I got it to handle every form of color map. So you can run it in 1, 2, 4, 8, 16, 32 color. And sound, we did a good job. John Maloney did a lot of this work interfacing to the underlying sound buffers. And things were getting fast enough that we could do real-time music synthesis in FM or regular waveform. I guess, yeah, we did have Worklit running now. That's right. So Worklit is what was used when I rotated those windows. One of the greatest things I think in Squeak was that by having it all be in Smalltalk, it suddenly reduced the effort to do new primitives. So I never would have dreamed of doing Worklit if I had to debug it in something like C. But I actually got it running in the course of a 1-week offsite meeting. Offsite meetings when we got all our cool work done. Just because it was possible, just debug it in Smalltalk, but the Smalltalk debugger, they just stop it anywhere, see what's happening, and see it happening on the screen at the same time. And that also let us do the music in a really nice way, too. Yes, so that's about it. I mentioned about the compactness of the storage manager. So we had, we put a bunch of things into it, so it got to be larger, it got to be like a megabyte, and it's continued to grow ever since. But we did have one image that we put some effort into called the mini image, which was 600K, and it's got a complete IDE and rich text and 32-bit objects. And we got that running on the most fun thing we put it on was a chip that had been developed by Mitsubishi. And John worked with a Mitsubishi intern porting it. And what was notable about this chip was that it had both DRAM and regular silicon, so that you could actually have the memory together with the processor on the same chip. And I think the story goes that either Intel or Motorola bought the patents for it from Mitsubishi and then did nothing with it. But anyway, so we went for this demo at Mitsubishi, and the intern had actually put together the all the sort of real-time connections out from this thing. And Alan came along on this trip, and we got it running. It was hooked up to a display, and Alan said, "Oh, that's neat," and proceeded to give a drive-a-car eToys demo on this chip. So we all got luggage tags with an embedded chip from that, and nothing else, because as I say, the thing got very. But it was neat to have the entirety of Squeak running on a chip. I'll show you that image. Yeah, there it is. And it's what we keep looking at. What else can I show you about this? Well, if there's a story, I can tell you about this at least. Quick. Somewhere in a while after all of this, I tried to retire, and then I came back and started working at Sun Microsystems, and I spent a while, wondering what I'm doing in Temple of Java. But I did figure that I should at least learn Java. So what am I going to write in Java? A Squeak VM. So I did that, and then it looked like people were having a lot of fun doing stuff in browsers. So I found out that yes, there's a way to take a Java program and turn it into something that's like an applet. And let's see if I'm lucky here. Maybe I can make that work too. Okay. So this thing. Yeah. So there's a STIC applet that's running this same mini image. And that's like 400K because it's a jar, and jar is compact things. And it turns out when you make a small STIC image, all the direct pointers are zeros, so that the compactors do a good job with them. So same thing. But that was a lot of fun. And I think if I want, I need to quit it up here. Okay. So that project was called keynote because the people at I spent so long at Sun trying to get through the trademark people about what can I call this thing I want to release. And so I showed you that. So then, one of the cool things we did in STIC was image segments. Alan forced us to do all sorts of stuff. So he kept making more and more projects in this image, which got bigger and bigger, and it was getting up to 100 megabytes, which in those days was a big image. And plus, we had a wonderful storage manager, but 100 megabytes was starting to be a problem, although most of the incremental stuff worked. So I kept thinking, look, these projects that we made were pretty modular. And Ted had figured out a way to sort of disconnect most of the pointers and to sort them out as separate kind of files. And it seemed to me that there ought to be a way to just sort of find this glob and identify it quickly. And I had this idea, which turned out not to be original, but that if you use the garbage collector, and this is another case of, if everything's written in small, it's actually easy to work on the garbage collectors. That if you turn the mark bit on the top of one of these things and did a garbage collection pass of everything else, it would leave all the stuff below in the shadow of the trace phase, and you have identified this thing. The reason I know it's not original is I told George Bosler about it, and he said, "Oh yeah, we did that." We got that to work, and so there was that phase, and then the next phase would just copy all of this thing into another thing that looked exactly like an image. It was just very small, and that was what we called an image segment. And it was able to do stuff really fast. Like I remember being able to swap out or swap in the entire virtual memory simulator, which is like a quarter megabyte or more, in like a tenth of a second. So that was really cool. So that then became the basis of how we could swap in and swap out projects on demand. So that for a while helped with Alan's images. And I think what I'll do now is just take you for a tour of a couple of things that I like that are in these projects, and then I'll leave some time for questions. So let's see what we got here. So this is one of my old images that I still use for playing pre-cell. But here's an actual product that I built. It's a weather station, which I originally wrote in Visual Basic, and then when I came back and got STIC going, I redid it. And I sold some of those, and then I finally figured out that I could make more doing research than doing that. But it's kind of neat. It's keeping track of barometric pressure. It goes with one of these wireless or wired sensors. This is temperature. This is wind speed, wind direction, and little arrows. And that's the humidity. And this is the tide cycles. And this is a rain $50 grand. And you could, it's just running, it's sort of a little demo program, and I think I can make it run faster. Fast. Yeah. So this will give you some sense. This is actually a storm that I recorded when I was in Virginia. And you can see the barometric pressure is going way down. And you can see the wind is coming out of the south, as it usually is when a storm's coming on. And here is the rain coming down. And so that was a lot of fun. I won't bore you with going through the whole thing. Here's a fun thing, I think. This was Ned Kuntz. Ned Kuntz did a refrigerator magnets program. Yeah, so you could move these things around, and when you put them there, they push them. So I saw that, and I thought, there's something I want to do with that. So this was when my son Charlie was sort of learning to read, and so you could take and do. Let's see. Now I've got to find a K. That's a K. So, and this also put together Luciano Nota Francesco in Argentina did the speech synthesizer. I thought that was really neat. And then I got this other idea when we got into numbers to do this.
7,865.
So, and if you put
27,865.
And this is a great thing for kids because, kids, what if I make it bigger? And it just doesn't mind.
727,865.
You get the idea. Let's see. Oh, here's one of my favorite. I was going to say hacks. It's not. It's a beautiful thing that Ted did. So this is the method finder, and so you could do things like you could type in ABC, the string ABC, and 3, and it would come back with it could have been you could have been sending the message basic size or the message size, and you would get that result. And you could do things like
Expand the screen.
Yeah, thank you. Yeah. Exactly. Yeah. Makes it better for me too. You could do things like 3, 4, and 7. And it tells you, well, it could be plus, or it could be bit or bit XOR. Right?
Very mysterious. I always found that thing very mysterious.
And you could do things like small SM. What's the way that you find out that something begins with something, right? Well, there are all sorts of things. It could be that SM is less than small or less than or equal to small. But there's the one we're looking for, which is begins with, right? But it gives it to you. And it's complete magic. Only Ted would have thought of doing this. I'm not going to explain it. It is so useful. In a system that people don't know, search is the most valuable thing you can possibly have. And I'm thinking of putting that into the lively kernel. What's that? So let me just show you a couple more things, and then we can have time for questions. And I'll start up this one other image which has some problems. Oh yeah, it's got such problems. It won't start up that way. Let's do this one more try. Oh. I'm not sure what's happening for this. Let me just see. I think I may need to do this. Yeah, which one? That's really surprised. Just bear with me for a minute. See if we can get this done. Those guys are good. Okay. So, what's that?
Just start up another one. Don't worry about the dead one.
Yeah, but I tried that here. And it didn't work. So what I've got to do here is to kill off. I see that. I see that. Okay. There we go. I think. Yeah. So this is showing Squeak in action about the time of when we showed it at Oops Live. And we had gotten, Alan said, can't you make text work nicely and do, stream from one part to another? So I took him at his word and said, yes, I can do that. So actually made runaround text work. And then we did these nice little transitions like that. It's all bitlit, I tell you. That whole thing about text runaround is bitlit, counting the bits and figuring out where the lines can go and stuff. Just incredible hacks. So then, this is my favorite thing that I did with that. So this is, here we have, in addition to runaround text, it would also fill up a polygon. And then I did this, which is complete. So you can, this thing, it's connected like a pipe, so you can do this. See how that's working? And you could take, actually, that's worth seeing a little closer. And then you could, grab a hold of that pipe and pull it out. I can't remember if you can certainly type here. You want to type in here? Yeah. Thank you for asking. It's been a while. Okay, and then let me show a couple of quick things. So a couple of things. I want to show this. This was some of the cool stuff that Andreas Robb did. He did a whole vector rendering package in Squeak, and this is showing a piece of Disney material that I shouldn't be showing, but it shows how that works. And that became a lot of the 3D stuff in Croquet. I think, and let me pick a simple one of these. Here's the whole eToy system that we did in Squeak. Allows you to program with tiles, and the tiles basically represent small talk code. And this is a simple simulation of gears that Alan did. I think it's really cool. But basically, if you look at the rules, the gear on the left just keeps turning by 1. Okay, and then this gear looks for whether its blueness overlaps the color red, and if so, it turns by -1. And the green one looks to see if its green color overlaps the blue color, and if so, it turns by 1. And I think I'm going to have to sound quiet when I do this. And let's move that tab over. And if we started out, there it is. Isn't that cool? So that's end user programming in Smalltalk. So I think that's enough to give you an idea of the tile scripting. And now what I want to do is to show you this thing. This to me is one of the coolest things that was ever done in Squeak. And I'll just rewind it. So this is, what do we have here? We've got a MIDI score being played and synthesized. Right. And you know what I want to do is see if I can do this. Go to full screen. And so these guys, there's 3 players here. The clarinet and the trumpet and the trombone. And if you grab a hold of them, if you move them nearer and farther, they get bigger and smaller. And this is the clarinet, and I think the clarinet doesn't come in for a little bit. But take a look at the slider for the clarinet, the left, right pan, and the volume. Alan did this. This was really cool. And I'm going to pause and go forward to where it is. I've got some. And if you look at how it works, you could also edit the timbre of the instruments while it's running. These are the tile scripts that here you can see that so here's where the scale factor gets changed, for doing that, and here's the controlling the level slider and the pan slider. Some of this is getting right, so so I'll just trim that down a little bit and take questions. So it sounds like you're talking about fabric. Yeah. Yeah, so I did that one in Apple Smalltalk. And then I did another one, Some Things Never Leave You. I kind of got that working in Sweep as well. And I'm going to keep doing it because at some point, I want to get it so that you can actually build all the little widgets that you do that way. But there are real limitations to wires. And I'm actually working on something just like that in the lively kernel now, too. Yeah?
Yeah, I'm wondering what version of Smalltalk had the first, was the stepping debugger first implemented, and who did that?
That was Smalltalk 76, I believe. Yeah, because we had that was the first time we had context written in Smalltalk we could step on.
There was actually a Smalltalk 74, which gets lost.
Yeah, that's right. Yeah. So, and Dave worked on Smalltalk 74 especially. Smalltalk 74 was an attempt to take. I showed you how the stream parsing worked in Smalltalk 72. A lot of those were primitive. Smalltalk 74 made the stream parsing actually be in the programming language, I think. Or do you want to clarify that? I kind of forgot.
Yeah, but it also, right, it made a real, classes were instances of class, and activations records were instances of.
Oh, so I had forgotten that.
Yeah.
I'm glad you reminded me.
And the problem was activation records were actually allocated out of the heap.
Yes.
Right, which was good for programming and bad for execution.
That's great. Yep.
But I think that's where you could start to write. Right, you could start to define the class of contexts.
Yep. So that.
Browsers were done first in Smalltalk 74.
But again, it was slow.
Yeah, and I think it never saw much use because everybody was using Smalltalk 72. Right. And then we started working on 76. I'm glad you reminded me of that. Yeah. Question? Yeah?
I just wondered if you could tell us a little bit more about recent, like the library kernel, and especially what you're doing inside.
I wouldn't want to take up too much time here talking about the JavaScript. I will show you one thing now, since you asked. Let's see what we got here.
The LGD was online.
So this is the library kernel. It's a web page. But one of the things there's lots of stuff that we brought into Lively, and one of the things is the OMeta compiler, and written in JavaScript. And so here's a little demo. Oh, I can get rid of this everything. Let me see. Well, no, you need to see the stuff down below too. So here is a Smalltalk collection running the collect method. Right. 1, 2, 3, 4, 5, collect 5 times 2. Keyword syntax. And if I do a print it, there's the result. Here's one that says world morph current set fill color R:, G:, B:. And I don't know what this is, I've forgotten. Oh, it's some ASCII art thing. Oh, I forgot to tell you, so down below, in this pane here, it's showing you what it translated to in JavaScript. And this next one here uses some of the Lively kernel stuff to go out on the web and find the temperature in Palo Alto, and I ran it before, and I know that it's got BitRock because Google changed their API there. But this one still works. So this says world morph current get submorphs for each. Take that morph and at velocity put global PT random, okay, and at angular velocity and start stepping, step and bounce. What do you think will happen if I execute that?
me.
So, somebody asked about spinning the windows. Yeah.
Does it have an undo button?
Nothing with that. Yes, you read it. So the browser even supports it. Any other questions? Okay, thanks.